Hello everyone, welcome to Algo-holic, the place where you learn not just the solutions but the thought process behind solving problems. Today we're solving the problem remove duplicates from sorted array part 2. We are given an integer array nums sorted in non-decreasing order. We are supposed to remove the duplicates in place such that each unique element appears at most twice. The relative order of the elements should also be kept the same. This is a continuation of the previous problem where we were supposed to remove all duplicates from the array. Here we can have duplicates as long as they appear at most twice. Since we're also supposed to solve this problem in place, this part of the question talks about what value needs to be returned. We are supposed to transfer all the unique elements in the array to the start of the array and return the value k, where k signifies the number of unique elements in the array. Let's look at an example to understand better. There's an array which has 1, 1, 1, 2, 2, and 3. Since there are 3 occurrences of 1, we remove one of the ones, and the final array is going to be 1, 1, 2, 2, and 3. There's a blank at the end which tells us that the testing algorithm is not going to look at that part of the array. So we can use that for any calculation, or we can use that for storing any dummy values. This is because the output that we are going to return is 5. So the testing algorithm is only going to look at the first 5 elements. Let's look at an example again, where we have 0, 0, 4 times 1, 2, and 3, 3. So since 1 is repeated 4 times, we remove 1, 1, and the final array is going to be 0, 0, 1, 1, 2, 3, 3. There are 7 elements, so we return the value 7. This is the gist of the problem. And how do you go about solving this? Well, the brute force approach is to just pop out elements from the array. So let's say we have an array like this, 1, 1, 1, 2, 2, 2, and 3. We maintain a count variable. So every time the count variable exceeds 2, we just pop out those elements from the array. So when the pointer is over here, it's going to be 1. Here it's going to be 2. Here it's going to be 3, since this is the third occurrence of 1. So we just go ahead and pop out 1. What I mean by popping out is just calling the default pop function from Python, Java, or C++. So when you pop out that element, the array is going to look like this: 1, 1, 2, 2, 2, and 3. Now the count variable again becomes 1 over here, since this is the first occurrence of 2. Here it's going to become 2. Here it's going to become 3. So we pop out this 2 as well. And the final array is going to look like this. After we reach this step, all we have to do is return the length of the final array. Now, what is the time complexity of this? Well, the time complexity of this is going to be O of n square. This is because every time we pop out an element from the middle of the array, all the elements towards the right of it needs to be copied over so that the index is still accessible. So here it's going to become O of n. Again, we pop out 2 over here. This is again going to become O of n. So let's say there are n elements that needs to be popped out. The time complexity then would become O of n square, because we have to perform this copying n times. So how do you go about making this more optimized? We can use the approach that we used to solve the previous problem, where we had 2 pointers, slow and a fast pointer, and the slow pointer would be stationed at the index which needs to be replaced, and the fast pointer will go ahead and look for a value that needs to take its place. I'll quickly go over the algorithm. Let's say we have an array like this. Slow and fast both pointers will be initialized. So we check if 1 equals the previous value. There is no previous value, so we move both the pointers. Now we check if 1 equals the previous value. 1 does equal the previous value, so we keep the slow pointer at the same place and we only move the fast pointer. Now we check if 2 equals 1. 2 does not equals 1. So what does this mean? This means that we found a new element which needs to take the old element's place. So we take the value of the fast pointer, we put it to the slow pointer's position. So 2 is going to be here. So the array is going to look like this, where we have 1, 2, 2, 2, and 3. The slow pointer is over here and the fast pointer is over here. So we increment the fast pointer and the slow pointer since we just made the switch. So the slow pointer is here and the fast pointer is over here. Now we again check if 2 equals the previous value. It does. So we move the fast pointer. Now we check if 3 equals 2. 3 does not equals 2. So what would happen over here. We take the value of the fast pointer, we put it to the slow pointer's place. So this is going to become 1, 2, 3, 2, and 3. In the end, we just return the index of the slow pointer. So in this case, it's going to be 3, which tells the testing algorithm that the first 3 elements in the array are unique. So this doesn't matter. So this is simple when we have to find and remove duplicates. But how do you use this approach to solve the current problem where we can have 2 elements which are of the same value? So let's modify this algorithm to meet the needs of the current problem. In the previous problem, since there were no duplicates allowed, all we had to do was check if the current value equals the previous value. Here, there are 2 instances allowed of every value. So we are supposed to check if the current value equals the value at 2 indexes before the current index. By doing this, we are essentially asking if there are 3 consecutive elements of a particular value. Let me write it down so that it's easier to visualize. Let's say this is the array. So before we were checking if the current value equals the previous value. Here we are checking if the current value equals the value at 2 indexes before the current index. So here it's going to overflow. We move the pointers over here. This is again going to overflow. So we move the pointers over here. Now we check if 2 equals 1. 2 does not equal 1. So we move both the pointers. We again check if 2 equals 1. 2 does not equal 1. So we move both the pointers. Now we check if 2 equals 2. 2 does equals 2. So what happens now? We keep the slow pointer and we only move the fast pointer. Now we check if 3 equals 2. 3 does not equals 2. So what happens now? We take the value at the fast pointer and move it to the slow pointer's position. So the final array is going to be 1, 1, 2, 2, 3, and 3 again. But since the slow pointer ended over here, we are just returning this part of the array. The testing algorithm will ignore the final value. So this is pretty much it. But how is this more efficient than the popping method? Well, as opposed to the popping method, here every element will be copied to the left side of it at most once. So what do I mean by that? Here you can see 3 was copied to 2's place. Now when 3 was copied to 2's place, the final array was this. So no matter how many elements were present in the array, this part of the array was not going to change at all. So this is what I mean by every element will be copied at most once. So once this is done, let's say there were another element over here, let's say it was 6, another element over here, let's say 7, something like that. So in the popping method, even the 6 and the 7 had to be copied towards the left since the whole array index needs to be accessed. So we copy 6 and 7 towards the left at every pop before it. But here, we are not going to copy 6 and 7 until the fast pointer reaches 6 and 7. So by doing this, we are copying every element at most 2 times. Sorry, at most once. So the time complexity will be big O of n plus n, which is going to be 2n, and we can just round it down to big O of n. And we're not taking any extra space, so that's going to be constant space. Let's quickly code up the brute force solution. So I is 2, while I is less than nums. We check if nums I equals nums I minus 2. If it does, all we have to do is pop it out. If it does not, we increment the value of I. In the end, we return the length of nums. Now, why are we writing I plus 1 only in the else block and not in the if block? In the if block, since we are popping out an element from the array, the pointer will already be pointing towards the next element. So I'll just show you what I mean by this. Let's say we have 1, 1, 1, 2, 2, and so on. And the pointer is pointing towards the third instance of 1. So we pop it out, and the new array is going to look like this. As you can see, the pointer is already pointing towards the next element. If we were to write I plus 1 again, the pointer would be pointing at the second instance of 2, which would have overshot the first instance. So to avoid this, we only write I plus 1 in the second instance, which is the else block. So this should work. Yep, it does work. Now let's look at the optimal solution. So slow starts at 2, for fast and range again from 2. So in the previous algorithm, what we were doing is we were checking if nums fast is not equals to nums fast minus 1. So you would think that in this algorithm, all we have to do is change this from fast minus 1 to fast minus 2. But this is going to fail. I'll show you why. So we make the replacement. After we make the replacement, we increment slow, return the value of slow. Now this is going to fail. Did fail. So all we have to do is change this from fast minus 2 to slow minus 2, and it is going to work. It did work. Now, why does this happen? I'll show you with an example. Let's say we have 1, 1, 1, 2, 2, and 3. So we initialize both fast and slow pointer here. We check if 1 equals 1. It does not equals 1. Sorry, it does equals 1. So what happens? Fast pointer moves and slow pointer remains in the same position. So fast pointer is over here now. Now we check if 2 equals 1. It does not. So what happens? The value of the fast pointer will be taking the slow pointer's place. So this is going to be 1, 1, 2, 2, 2, 3. Now, as you can see, we got 3 instances of 2, but in the original array, there was just 2 instances of 2. Now, how does this affect the outcome? We'll see. So the slow pointer is over here and the fast pointer is over here. We increment both of them. So slow comes over here and fast comes over here. Now we again check. Now 2 is equals to 2. So what happens? We only move the fast pointer. Now we check if 3 equals to 3 does not equals to. What happens now? We make the switch. So 3 goes over here. The final array is 1, 1, 2, 3, 2, 3. And the slow pointer is over here. So this is the final array. As you can see, there were 2 instances of 2, but in the final array, we just got 1 instance of 2. So this is the mistake, and this is why the algorithm is failing. Now let's look at what would happen if instead of comparing fast minus 2, we compare fast and slow minus 2 like we did in the code. So we'll take the same example. We have 1, 1, 1, 2, 2, and 3. Both slow and fast are initialized over here. We check if 1 equals 1. Now 1 does equals 1. So what happens now? We move the fast pointer. Now we are checking if fast equals slow minus 2. So if 2 equals slow minus 2, which is 1 over here. So we're checking if 2 equals 1 over here. It does not equals. So what happens? We make the replacement and we move both the pointers. So 2 comes over here. The final array is 1, 1, 2, 2, 2, and 3. We again got 3 instances of 2, but this is going to work. So the slow pointer was over here and the fast pointer was over here. We move both of them. So slow comes over here and fast comes over here. Now we again check. We check if 2 equals slow minus 2, which is slow minus 2, 1. So we're checking if 2 equals 1. It does not equals. So what happens now? We make the switch. So 2 takes the place of 2 again. So this is not going to be of there's not going to be any change because 2 and 2 is the same. So this is going to be 1, 1, 2, 2, 2, and 3. But both the pointers are going to be moved. So the slow pointer is going to be here and the fast pointer is going to be over here. You did not see any change because we took this 2 and we put it over here. So there's no change. Now we are again checking if the fast value equals slow minus 2. So we are checking if 3 equals 2. Now 3 does not equals 2. So what happens? The value of 3 goes over here. So the final array is 1, 1, 2, 2, and 3 and 3. Since the slow pointer was over here, the final array is 1, 1, 2, 2, and 3. So this is the correct answer, and this is why we are supposed to compare the fast value with slow minus 2 instead of fast minus 2. C++ and Java code looks pretty much the same, similar to the previous problem where slow, instead of being initialized to 1, it's now initialized to 2. And instead of checking nums fast and nums fast minus 1, we are checking nums fast and slow minus 2. And we're returning the slow in the end. Java code looks pretty much the same where initialization and the comparison and swap, and we're returning slow. So that's all for today. I hope you found this video helpful. Your feedback helps me make better content. So please share your thoughts in the comments below. I'll see you in the next one.